We can change the state of motion of an object by changing its speed, its direction, or both. Acceleration is the rate at which the velocity is changing. In physics, the term acceleration applies to decreases as well as increases in speed. Acceleration also applies to changes in direction. It's important to distinguish between speed and velocity. Acceleration is defined as the rate of change in velocity, not speed. Acceleration, like velocity, is a vector quantity because it's directional. When you accelerate in the direction of velocity, you speed up. When you accelerate against velocity, you slow down. When you accelerate at an angle to velocity, you change direction. When straight line motion is considered, it's common to use speed and velocity interchangeably. When the direction isn't changing, acceleration can be expressed as the rate at which speed changes. Speed and velocity are measured in units of distance per time. Acceleration is the change in velocity or speed per time interval. If you change the speed from 0 kilometers per hour to 10 kilometers per hour in 1 second, acceleration along a straight line is 10 kilometers per hour per second. Note that a unit for time appears twice, once for the unit of speed and again for the interval of time in which the speed's changing. Let's do another example. A girl's driving her car at 30 meters per second when a ball rolls out into the street in front of her. She slams on the brakes and stops her car in 3 seconds. What was the acceleration of the car? What we're looking for here is the acceleration of the car. That's the variable little a. That's what we don't know. Now what do we know? I see 2 numbers here. I see 30 meters per second and 3 seconds. 30 meters per second, by the unit, that tells me that our speed is 30 meters per second. Meters per second is a unit of speed. The other one is 3 seconds. Seconds is a unit of time. So I now know 2 pieces of information. I have something that I want to know. I need a relationship between those in order to solve for the acceleration. And the acceleration is part of a relationship that says the acceleration equals the change in speed over the time. Now here, I have the speed her car was going before it stopped. That's not the change in speed. What we need to find a change in speed is 2 speeds. A change in anything is the final minus the initial. So what I need is the final speed and the initial speed. This happens to be the initial speed, and the final speed, if we read very carefully, where she stops her car, is 0. So that means my change in speed is actually 0 minus 30 meters per second. Another way of thinking that is that she lost 30 meters per second worth of speed. And it took her 3 seconds to do this. And if we do the math here, negative 30 over 3 is minus 10 meters per second squared. And that is the acceleration of our car. Imagine there's no air resistance and that gravity is the only thing affecting a falling object. An object moving under the influence of gravity only is said to be in free fall. During each second of fall, the instantaneous speed of the object increases by an additional 10 meters per second. This gain in speed per second is the acceleration. When the change in speed is in meters per second and the time interval is in seconds, the acceleration is in meters per second squared. For free fall, it's customary to use the letter g to represent the acceleration because the acceleration is due to gravity. Although g varies slightly in different parts of the world, its average value is nearly 10 meters per second squared. Where accuracy is important, the value of 9.8 meters per second should be used for the acceleration during free fall. The instantaneous speed of an object falling from rest is equal to the acceleration multiplied by the elapsed time. V equals g times t. The letter v represents both speed and velocity. When the acceleration g equals 10 meters per second squared is multiplied by the elapsed time in seconds, the result is the instantaneous speed in meters per second. If a falling rock were somehow equipped with a speedometer, in each succeeding second of fall its reading would increase by the same amount, 10 meters per second. Now consider an object thrown straight up. It moves upward for a while. At the highest point, when the object is changing direction from upward to downward, its instantaneous speed is 0. It then falls downward if it had been dropped from rest at that height. During the upward part of this motion, the object slows from its initial upward velocity to 0 velocity. The object is accelerating because its velocity is changing. How much does its speed decrease each second? The speed decreases at the same rate it increases when moving downward, at 10 meters per second each second. The instantaneous speed at points of equal elevation in the path is the same whether the object is moving upward or downward. The velocities are different because they're in opposite directions. During each second, the speed or the velocity changes by 10 meters per second downward. The change in speed each second is the same whether the ball is going upward or downward. How far does an object in free fall travel in the first second? At the end of the first second, the falling object has an instantaneous speed of 10 meters per second. The initial speed is 0 meters per second. The average speed is 5 meters per second. During the first second, the object has an average speed of 5 meters per second, so it falls a distance of 5 meters. Pretend that a falling rock is somehow equipped with an odometer. The readings of distance fallen increase with time. At the end of 1 second, the rock has fallen 5 meters. At the end of 2 seconds, it's dropped a total distance of 20 meters. At the end of 3 seconds, it's dropped 45 meters altogether. These distances form a mathematical pattern. At the end of time t, the object starting from rest falls a distance d. We use freely falling objects to describe the relationship between distance traveled, acceleration, and velocity acquired. The same principles apply to any accelerating object. Whenever an object's initial speed is 0 and the acceleration a is constant, velocity and distance traveled are v equals at and d equals 1/2 at squared.